Hello, this is Phil Thomas, New Era Systems. Today I want to look at cross-guide couplers. Cross-guide coupler is a very useful device that I use all the time to test amplifiers. It's a way of getting the output from the amplifier into a device where I can measure it, either measuring the frequency or measuring the power output. Now there's two different cross-guide couplers here, but basically they are the same thing. When you look at this closest cross-guide coupler, it's not immediately clear which side goes to the amplifier and which side goes to the dummy load. The bigger one you can see because I've already set it up accordingly. But this is a little bit more subtle. If you look at this line, it indicates that the power is coming from the amplifier and it's going out to the monitor port. So the dummy load attaches here, and this side goes to the amplifier. So that's straightforward. The same thing is true of this 3-port cross-guide coupler. But there's a couple of interesting things here. If you look at these arrows, those two are going in one direction, this is going in another direction. And again, if you follow the arrow, in this case we're coming from the amplifier and we're going out to the monitor port, and the same here. We're coming from the amplifier and we're going out to the monitor port. This one is the reverse. In other words, it's expecting the power to come from this direction out to the monitor port, which is backwards. Well, it's not really backwards, because what this will allow us to test for is reflected power. RF radiation is not really like water in that it flows easily in one direction. It's more like light that can be reflected, and it can be reflected back from awkward turns in the waveguide or some sort of interference in the waveguide. And so it's often important in a teleport to be able to watch the reflected power, particularly on the large amplifiers. And that's what this particular port will do for us. Now the other interesting fact about this cross-guide coupler is when you look at these attenuation levels. Now it's obviously KU band, so looking at 14.05 gig, we see 36.5 dB attenuation. This is the one that tests reflected power. Going forward from the amplifier to the dummy load, we're seeing 36.5 again, but down here we're seeing 53. So in other words, port number 3 is attenuated a lot more than port number 2. Essentially they're both doing the same thing. But when we use power meters to test the output or to measure the output of an amplifier, sometimes the power heads are different, and some of them are more sensitive than the others. They may be a microwatt meter instead of just a standard watt meter, in which case you need the greater attenuation to avoid damaging the power head. That's why it's particularly important to have different levels of attenuation on these. Now what I'm going to do, I'm going to attach this cross-guide coupler to this amplifier. It's a Comtech 100 watt KU band buck. Connect one port to the spectrum analyzer and the other port to the Agilent power meter. And I can demonstrate the difference in the way that these two ports are going to be used. Okay, a few minutes have passed, and now I've connected the cross-guide coupler and the dummy load to the back of this amplifier. The amplifier is currently transmitting at about 20 watts, which is 1/3 of its power. I'm using this Agilent signal generator to generate an L-band signal. It's 1200 megahertz. Because this is a buck, it translates into 14 gig. One of my cross-guide monitor ports is connected to the power meter, the other one to the spectrum analyzer. On the power meter I've done two things. I've set it up to display at 14 gigs frequency, but I've also set up the attenuation to reflect that the cross-guide coupler has attenuated it by 53 dB, and all of that's been taken into account, and so the 20 watts that you see is an accurate 20 watts measured from the cross-guide coupler point. Look in the spectrum analyzer, you can see that the frequency is almost exactly 14 gig. It's off very slightly, but it's well within the margin of acceptability. And I've set it up so that I can test the intermodulation, or at least see the intermodulation. Not only does an amplifier have to output at an acceptable power level, it also has to be on target as far as frequency is concerned, and also something called intermodulation. And here you're looking for problems in the signal, artifacts that may affect the power to transmit. And normally the way we do this, we measure from the noise floor, which is that part there, up to the top of the signal. There should be 50 dB separation between the two to indicate that it is a good signal. In this particular case, as I look at it, it looks to be very good. I count down 1, 2, 3, 4, 5, 6, really 7 or 70 dB. So there's very little in the way of noise that would affect this when it's transmitting to the satellite. The satellite engineers would accept this as being a good amplifier and a good output. So the goal of this exercise was really just to discuss the cross-guide coupler. I think I've done that, and dipping into intermodulation at the same time. There's not much more I can say other than I'm wrapping it up and turning off this amplifier now.